Hello everyone, welcome to this video. My name is Amir Senahari. I'm a Google Earth Engine expert. Today I'm going to show you how to do anomaly detection for precipitation data in the Google Earth Engine platform, spatially and temporally. It's a very important topic for the climate change related studies and climatological data analysis. So let's go to the Google Earth Engine platform. In the first step, identify your study of interest or region of the interest. By the drawing tools here available, you can identify your region of the interest. For example, I prefer to select a part of Iran as my own country. For example, in the north of Iran, we have more precipitation during the year, and then I prefer to select a region from this part of my country. And also you can do this tutorial for all around the world, no matter which area you are selecting, and also it doesn't matter which kind of country or which kind of province you have selected to do for your analysis. So in the first step, we need to have focus on our study area by the map.center object here. So map.center object including the geometry. I want to run the code, and once the code is run, select or show my study area by the geometry. It's an optional script, and also you can also remove it from your code, but would be better to use it because when the code is run, it has focus. It helps you to have focus on your study area, and you don't need to scrolling on the map to find the desired the location that you already selected. So in the next step, we need a variable to call precipitation data. Through the search places and dataset, you can have access through the browse data catalog. You can go to the data catalog and search through the tags about the precipitation and rainfall. For example, in filter dataset tags, if you write precipitation for more than 40 dataset available here, go to the precipitation dataset, and some of them directly estimated from the satellite data and some of them assimilated. The assimilated products coming from combination of remote sensing satellites and models and in situ data. For example, GLDAS is one of the assimilated products that coming from the combination of the remote sensing and in situ data measurement. So in this tutorial, I'm going to show you the highest spatial resolution for the precipitation data that is available by the CURPS dataset. So here, if we scrolling and browsing, for example, by Control F, I can find the CURPS daily precipitation data. You can see that it's daily available, the daily temporal frequency available since 1981, and also with 5 kilometer pixel size. It's valuable for the climatological data analysis. As you know, for the climatic variables, because of the high temporal frequency and also the kind of or satellite orbits, we can't have a high spatial resolution. In the Google Earth Engine, for now, the highest spatial resolution for the precipitation data is 5 kilometer that is available through the CURPS dataset. And you can use it in your own code by the daily frequency, and also its real time is available, and you can use it for your process related to the climate change or something like that. So back to your code, through the search places and dataset, you can write the CURPS, the name of the product or the name of the satellite you are going to use. So here I try to write it, but here we have it, CURPS daily satellite data available, then import it into the code and consider it as an image collection here. Then I make a variable with the same name and assign image collection to the CURPS variable. So for the next step, we need to set the time start and time end through the filter date. Filter date, as you can see, 2 variables needed here, one time start and one time end. So we have time start first equals to, for example, 2000. I want to do precipitation data analysis for 20 years, from 2000 to time end equals to 2020. And also you can do or repeat these processing steps for the data coming from 1980 to 2020 or more. It depends on the spanning time that you considered for your study. So, as this is a coarse spatial resolution data, you don't need to set filter bound for this product. So, in the next step, we need to convert the daily data into the monthly format because I want to do anomaly detection based on monthly frequency. When I turn the data to the monthly format, the number of images reduced and the trend of changes can be detected much easier than daily data. So here, for example, I make another variable. Here we need a function actually to convert the daily data to monthly format. So I want to make a function. It is Temporal Collection. If you are following my tutorials on the YouTube page, you can see that I always using a Temporal Collection function that is developed by the Google developers, and also it's very useful and helpful function enabling us to convert the satellite data from daily, weekly, monthly to the bigger temporal scale. For example, here I'm gonna convert the daily data to the monthly format. It's very useful because the daily data has a limit of processing for 5,000 images, and when we convert it to the monthly format, we have more space to do the processing. And also in my experience, when we turn the data from the daily to monthly, we can see the anomalies much easier and better than the daily data, and also we can interpret them really easier. So the temporal collection including multiple arguments. The first is the collection, and the next is a start, and then we have count, the number of output images we expect to have, and the interval, the temporal distance or the temporal difference between two images, and the unit of outputs, the temporal unit of outputs. Output image collection is important. So in the first step, in the body of function, I need to make a list of sequence actually by Earth Engine. That's list of sequence. There are a couple of arguments here. One of them is a start. Here we want to have a list starting from 0 to the end. The end is the number of output images expected in this code. The number of output images is count, and as the counter starting from 0, we need to subtract the count from 1, and the rest of arguments are optional and no need anymore. Another variable is origin date. The origin date is gonna be set through the start, but as the start is a string value, we need to convert it from a string value to a date format. EarthEngine.date is a good function helping us to convert the string date, the string values actually, the string value into the date format. The start here converted to the standard date format. Then we need to have the sequence of outputs, the sequence list that is created for the output into image collection format. EarthEngine.image collection. So here we have a sequence in the form of image collection. And now for each row in this sequence, or for each record of the sequence, we need to identify a time start and a time end. So to do this, we must make a loop through the map and then a function that each row or each record consider it as an I in this code. So now we have the start date, the first important variable here, that a start date calculate like this. From origin date that's already converted from string to the date that advance. Here we need to identify the delta or temporal delta and its unit, and time zone is an optional. Keep the unit as same as it is, and the delta should be replaced by the interval Earth engine dot number interval dot multiply I should be applied on each record. So next is, sorry, I write the next, it's wrong, and here we should have the end date. In the end date, again, origin date that advance with a little change, Earth engine dot number interval dot multiply Earth engine dot number, the number of the record, dot add 1. So then we have a unit here. Okay, and finally the function returns the input collections for a specific period of time that is already defined by the start date and end date, just like that. But during this time, we need to get we need to aggregate data through a statistical function. The statistical function here could be the average, minimum, maximum, and the sum. As I mentioned earlier in the previous videos that I was working with the precipitation data, I said that for the precipitation, when we want to convert it from the daily to the monthly or to the annually, we need to convert it to this or aggregate it through the sum function. So for the output, sum of each period or sum of each month, we need to have system time start and system time end to be able to do time series analysis in the next step. That is very important things for the output we are getting from this function. That set system time start equals to start date, but the start date should be converted to the millisecond, because the millisecond is a standard format for the date that Earth engine uses for the time series analysis. And then again, that set, this time we have system time end date equals to end date dot millisecond, just like that. It's very easy. It's very easy to use, and also the code of this tutorial is also available in my GitHub pages. And also, if you are watching this video in my YouTube page, below the video, actually there is a part of the explanation or description for this video. In there, I put the link for my GitHub, and you can have access to this code through the GitHub, and also try to learn it and also use it in your desired project. So now make a new variable. The new variable would be monthly data. So here we have the temporal collection as we mentioned earlier, but here the temporal collection including 5 arguments, and instead of argument must be replaced by a new variable. Instead of collection, we have CURPS data. Instead of start, we have time start. Instead of the count is important. So we want to have 20 years. We will have 20 years. And for each year, we need to have 12 months. So it's very simple calculation. For 20 years, we want to have 12 months. Finally, we need to have 240 months to cover 20 years. So instead of the count, we will have 240 and with 1 month interval. Instead of the interval is 1, and replace the unit with months, just like that. It's very easy and applicable technique for conversion of precipitation data to different temporal units. So now print monthly data. Printing technique helping us to see if there is any missing in our code, if there is any syntax error in our code or not. Run the code, code is running, and result is generating. For example, here we have 240 elements that is available for all dates. We have one band. If for one date you have 0 band, it means for one date you have missed information. So back to the code. After getting the monthly data, we want to get the precipitation anomaly values in the Earth Engine platform. There are different equations for the anomaly detection through the precipitation data. One of the most common technique is get the subtraction between the precipitation of the each date and the long-term average. For example, if we subtract precipitation for time t from the mean of precipitation for a long term, this is a typical technique that helping us to see that how much precipitation of each month go above or drop below the average of long term. It's very simple technique. So for example, we can try it now. For this technique, or for the anomaly detection typical methods, actually we need to have the precipitation average for a long term, for 20 years. So make a new variable for that, precipitation average equals to, so here get the monthly precipitation values and calculate the average of precipitation for each pixel in our study area. So if I print this map.addLayer PR_mean, you can clip it based on your region of the interest or geometry, and I leave the visualization properties empty, and then PR_mean is the name of the layer for the layer setting, and to avoid from automatic visualization, leave the false here. So save your code and run it. When the code is running, through the layers, you have a new layer entitled as average precipitation. When you check it on, after a few moments, you can see the average of precipitation for each pixel. So here, by the increasing the contrast by the 90%, the data converted to the normal range, and then through the apply, you can see that the precipitation changes over your study area. You can see that the brighter areas showing higher precipitation and the darker area showing lower temperature. For example, by the inspector, for a pixel here we have 52, meaning that the rate of precipitation in this pixel, the average of precipitation in this pixel over the last 20 years was 52 millimeter per month. 52 millimeter per month. So, and now I want to get the average. After getting the average for each pixel, we need to calculate the anomaly of precipitation for each pixel separately. So it's very easy. Just make a new function and get the difference between precipitation of the mean and get the subtraction between the precipitation of the each date to the average precipitation. So here variable anomaly equals to, so here we need to get the monthly data dot map into a function each input image considered, or each monthly input image considered as an IMG, and then in this function we will have a subtraction of each input images of dot subtract precipitation average. And for each output we need to have temporal information by dot copy properties from input images to the output. img dot property names, just like that. It's very easy. So now if you plot the precipitation changes for some dates or some months, you will have positive values and some months negative values. Let's see. Print user interface dot chart dot image dot series is a function helping us to aggregate the precipitation value over the study area or a spatial aggregation and see the variation over the time. Instead of image collection, we have anomaly. Instead of the region, we have the geometry. Here we want to do a spatial aggregation to aggregate a spatial the distribution of precipitation value into an average. For example, Earth engine that reducer, that's mean. Instead of a scale, we have the spatial resolution, for example 5 kilometer, 5,000 meter. Instead of property, x property, we need to have system time starts. And to have a better visualization for precipitation data, as I mentioned in another YouTube tutorials in this regard, for the precipitation data, because of the discrete nature of this kind of data, we need to have, would be better to use column chart. So by the column chart, then we run a code, and code is running, chart is generating in the panel right side under the console menu. After a few moments or after a few seconds, you will have an anomaly of precipitation for different dates. It is a monthly format. As I mentioned earlier, the range of the values for the anomaly data ranges from positive values to the minus values. And also you can see that for some dates values are positive and some dates the values are negative, meaning that, for example, in the positive values, meaning that the rate of precipitation in that specific month was higher than the long-term average. And also for those of dates, we have a negative value, meaning that the rate of precipitation in that specific date was lower than the long-term average. So it's very useful things to interpret the precipitation changes when we have higher precipitation, when we have lower precipitation. So for example, as you can see, this column is for February 1st, 2012. In the February, the rate of precipitation was higher than the long-term average, meaning that we had a heavy precipitation in this time or in this month, and also it's a totally wet month for this region. And in another column, for example, in January 2019, we have a positive value around 90. It means meaning that the rate of precipitation in this time in January 2019 was higher than the long-term average. So, or in this date, in July 1st, 2017, the minus value showing that the rate of precipitation in this date was lower than the long-term average. So you can see that the anomaly detection for the precipitation data is very helpful technique to understand the precipitation changes during a time. So back to your code. And also you can have access to the raster format of this output. It's very simple because already it is calculated by the anomaly variable and also it has a spatial and temporal characteristic together. For example, if you want to see the anomaly map for a specific period, here we can use map.addLayer to do the visualization. For example, I want to do the visualization for anomaly images calculated for example, anomaly images for a specific year, for example, 2010. Here I use the filter date. Using filter date, I wanna see the anomaly images for the 2010. Then by the two bands, I make a stack of all images available for 2010 to have access to all of them in the layer setting. And then I will clip it based on the region of the interest and leave the visualization parameter empty. And also in the layer setting, turn the name to the, for example, anomaly for 2010, and avoid from automatic visualization by false. Save your code and run it again. After a few moments, you will have another new layer in the layer setting, including anomaly images for 2010. When you check it on, in the layer setting, you can see that all monthly data for 2012 for 2010 are available here. So you can see that, for example, this is from the January to the December. For example, I want to select this one for May 2010, then throw the stretching technique by the 90%, I will increase the contrast. So in the output, you can see that the values ranges from positive to negative values. The darker region usually have the minus negative values. For example, this region in Anomaly 2010, you can see that this for image 24 has minus 75. It means the rate of precipitation in May 2010 compared to the long-term average was much lower than the was much lower actually, and brighter region showing that the rate of precipitation in this date, in this month, was higher than the long-term average, or it was really close to the long-term average. You can see that these techniques are very useful to get to interpret the final results, and then you can download these images into your own system and do some sort of classification in the ArcGIS Pro and to do more visualization and also get more result on this. So, and maybe you have a question about how we can download this image into the Google Earth from the Google Earth Engine platform. It's very simple. Just throw the export image to Drive. You can get the export from from this raster layer that is created. There are different arguments that should be considered for exporting an image collection. The first is an image. So, for example, we want to get export from anomaly data for 2010 in a stack layer and clipped from the region of the interest. Just copy all this expression, and then the description is the name of the output. The name of the output could be something like that. It's up to you, and also you can use any name that you want to use. You can pick any names that you think is better to describe the characteristic of your data. So, for example, here I use precipitation anomaly for 2010. And then by the scale, you need to set a spatial resolution. The spatial resolution here is 5000 meter, And in the next step, the region of the interest should be introduced. Here is the geometry. And again, if you want to set a folder to get to save the outputs there in your Google Drive, you can define a folder here, test, or any other name you need. Or I make a new folder entitled as precipitation to save all of the precipitation data in there. It depends on you. You can pick any names you want. And another important thing is the CRS, defining the coordinate system for the outputs. If you want to have the WGS84, you need to enter this code EPSG 4326. This is a general code to use to set WGS84 for the outputs. So that's important to consider for the outputs to have a right coordinate and latitude and longitude value. So, and also in the final step, just you need to save your code and run it. After the code is run, through the task, you will have precipitation anomaly for 2010. Would be better to set float function at the end to avoid from some sort of errors in the saving process. Just click on run and run again, and the data is saving in your Google Drive. In the Google Drive, you will have access to the 15 gigabyte space for the outputs from Google Earth Engine or any other platforms that is connected to your Gmail. So after the color turn to the blue like that, it means the output is ready, and through the opening drive, you can have access to the output. Here we have precipitation anomaly for 2010. You can download it and bring it into the any GIS based software to do the further analysis. And also that was the very simple tutorial and easy to use tutorial about the precipitation anomaly detection. And I hope this video helped you to do the precipitation data analysis much easier. And also the code is available in the video description. There is a GitHub web page, and then you can click on it and have access to the code. Feel free to contact with me if you had any question, if you had any problem. Just put the comments below the video. I will check and answer. Thank you for watching us.